This chapter of logarithms and exponential functions culminates in this section where you get to apply this to real life type of problems. And so this kind of gives a motivation for why we still study logarithms and exponential functions. There are other reasons for them too, because they do show up in lots of science and engineering type applications. But anyway, I want you to see get an idea of where the continuous growth model comes in. So the example I like to use when I teach a regular class is comparing Hillsborough to Wilmington. And I know these numbers aren't quite right, but let's suppose that this year Wilmington has a population of 12,000 and Hillsborough has a population of 6,000. And that over the course of the year they both increase by 1%. So after 1 year, Hillsborough increases by 1%. That means 60 people are added. And Wilmington increases by 1%, which means 120 people are added to Wilmington's population. So the increase over here was 60. Wilmington, which has twice the population, increased by twice as many people, 120. So you can say that the increase was twice as much for Wilmington, not on a percentage basis, but on a body count basis. All right, well, with this idea, you can start to say that, well, look, the rate at which it's increasing is going to depend upon how many people there are in the population. Well, that's a variation problem. So you can state it this way. The rate at which a population grows varies directly to the amount present, or the number of people present. All right, so in other words, when you have twice as many people, it grows, the rate at which it's growing is twice as fast. It depends on how many people are there. Well, that's a variation problem from an earlier chapter in this course. So we have these keywords. It varies directly, the rate, and the amount present. Now, suppose I call the amount present P for population, or amount present. And the rate at which it's growing, what do I call that? Well, that takes us into calculus. And this, in calculus terms, we would say this dp, we call this dp dt. So that's the symbols in calculus. Now, this is not going to impress you a lot, since I doubt anybody knows calculus watching this video. Maybe one person's had it before. But this rate, which symbolically in calculus we write this way, and this means the derivative of the population with respect to time, or the rate of change with respect to time is how you interpret these symbols, varies directly to the amount present. So it's equal to some constant k times the amount present. All right, so here's the equation of variation. And it takes calculus to solve that. And so the solution is a formula that you need to know for this section. So when you solve this thing, we see that the population with respect to time, which is this, p of t though, I'm writing it as a function, is equal to p subscript 0 times e to the k t. Alright, so I need to write that down a little bit lower because it's not showing up on the video, is it? Alright, so p of t equals to p subscript 0 e to the k t. Alright, showed up that time. I've got my computer to the side here as a monitor, so I know what you're looking at. Alright, and it's a little sloppy, isn't it, what you're looking at, but that's a k and that's a t. Alright, so this is the solution to this problem by using a little bit of basic calculus. Once you learn a little calculus, it's actually an easy problem to solve. All right, so let's, this is the, we might call